Today we are going to look at the priority queue abstract data type. I'm going to motivate it with a scheduling example. Then we are going to look at what the data type is. We are going to see how to implement a priority queue with a sequence. Then the key thing today we are going to do is to introduce the concept of a binary heap, and we are going to see how to do procedures for insertion in a heap and a procedure called heapify, which we will be using in the subsequent classes to see how to delete the minimum element in a binary heap and for other operations on heaps. So we have a multi-user computer system. That's a system in which there are multiple users who can submit jobs at different points in time. We assume that when a job arrives, the user we know in advance how much time the job is going to take on the particular system that we have. Further, we are going to assume that the jobs can get preempted. That is, that the job is running, it can be stopped, some other job can be scheduled on the processor, and then later this job which was stopped can be resumed. One policy which minimizes the average waiting time of a job is what is called the SRPT. The SRPT rule. It stands for shortest remaining processing time. What this policy says is that the processor schedules the job which is the smallest at any point in time, which has the smallest remaining processing time at any point in time. So to begin with, this processor has a bunch of jobs. It will take the smallest job from amongst that bunch and schedule it. Maybe this job finishes, then it picks up the next smallest job in this collection it has and schedules that one. But suppose we have a job which is running, and then midway some other job comes in which has a processing time which is smaller than the remaining processing time of this job, the one that is currently running. If such is the case, then we are going to interrupt the currently running job and schedule this new job that came in. So this is the setting in which interruption happens, in which preemption happens. So this is just a motivation. We are not going to be looking at this SRPT rule any more carefully than this. But if you were to implement this kind of a policy, what kind of a data structure would you need? That's what we are going to look at. So first, we somehow need to maintain the remaining processing time of the unfinished jobs, the jobs that have not been completely finished. They are still with us. They still need to be scheduled for some period of time. We need to maintain that collection. Amongst these set of jobs, we need to find out the one which has the shortest remaining processing time, because we need that so that we can schedule the job according to the rule that we are following. When a job finishes, we would like to remove it from this collection, and when a new job arrives, we would like to add it to this collection. So these are the kind of operations that we need to do on our data structure to be able to implement the SRPT policy. So one data type which will let us do all of this is what's called the priority queue. So it is a data type to maintain a set of elements, each of which has an associated priority. The priority queue data type supports the following operations. The first operation is one of inserting an element. So X is an element. We are going to insert it into our collection S, so that the new collection is now going to be S union X. Of course, this element has a certain priority, right? So when we are inserting the element, we'll also have to take care of the priority of that element. The minimum operation returns the element of S with the smallest priority, right? So priority perhaps is not the best word here, because when you say each element has a priority, you would like to say that you would like to get the element with the largest priority. So it's a bit of a misnomer here, but that's what we'll work with. So in the example, in the scheduling example, it made sense to remove the one with the minimum processing time remaining. So we'll continue with the minimum. The priority really is a misnomer here. and then we have the delete min operation. The delete min operation returns the element with the minimum priority and also removes it from the collection. So, the way minimum and delete min differ is that while minimum only returns the minimum element, it does not delete it from the collection, delete min also deletes it from the collection. So, these are the three basic operations that a priority queue is supposed to support. Of course, there could be many other operations, like for all other container classes that we have seen so far. We have seen methods like is empty, is size, and so on, or size is empty, and so on. So, one thing that we require on the priorities is a total order, and let me come to that. So, recall a priority queue ranks its elements by priority. Every element has a priority. Priorities need not necessarily be unique, but they are totally ordered. That is, given two priorities, I can compare them. I can decide whether one is smaller than the other or larger than the other, or they are both equal. So, there is a total order which will, let us say, denote by less than or equal to on the priorities. These priorities need not be integers, they could be anything at all, but there is definitely some kind of a total order on these priorities. So, in particular, this relation less than or equal to is reflexive, that is, priority k is less than or equal to k. It is antisymmetric, which means that if k1 is less than k2 and k2 is less than k1, then k1 is also less than or equal to k2. Then k1 is equal to k2. This is a error here. Then k1 and k2 should really be the same. And it is transitive. If k1 is less than k2 and k2 is less than k3, then k1 is less than k3. Right? So, these are the properties of a total order relation, and we will assume that the priorities that we have satisfy a total order relation. So, the most general and reusable form of a priority queue uses comparator objects. So, what do I mean by this? So, recall that we said that in a priority queue, each element has a priority associated with it, and the priorities, there is a total order on the priorities. So, if I want to put any kind of an object into my priority queue, I should have a mechanism of comparing the priorities of the objects in the queue. So, we can have such a comparator object which will help us do this comparison. So, the comparator object, all it does is it specifies the methods which will help us compare two priorities. So, in this manner, we can ensure that our priority queue, that we would have one implementation of a priority queue, and we can use the same implementation to store any kind of objects, because we would also specify this comparator object which would help us compare the priorities of any two objects that we desire to put into the collection. So, the comparator abstract data type would include methods like is less than or equal to, is equal to, is greater than or equal to, and whether it is comparable or not. So, let us first look at an implementation of a priority queue using an unsorted sequence. So, recall the items that we are trying to insert into a sequence are pairs of priority and element. We can implement the insert by using, let us just say, insert last. So, the insert operation of the priority queue, to do this we will just insert the element, the item at the very end of our sequence. Right. So, in this case 6 was the element that was to be inserted. Let us say we went and put it at the very end. This takes only a constant amount of time. But if we do such a thing, if we always insert at the end irrespective of the value of the priority, then our sequence is not ordered anymore. And since it is not ordered, according to the priorities, we are going to have problems when we are trying to find the minimum or when we are trying to delete the minimum element, the element with the minimum priority from this collection. In that case, we will have to look at all the elements of this sequence. So, for instance, if I have to find the minimum, then I would have to start right from here and traverse the sequence till I reach the element with the minimum priority, which is, let us say, a 1 here. That is to find the minimum. Similarly for delete min, because I will have to get to here, I will have to remove the element, and then I would have to find out the new minimum element. So, the worst case time complexity of minimum and delete min therefore becomes order n. So, that is not very good, right? Although insertion takes constant time, we are saying that both for minimum and for delete min we are going to take order n time. So, how about using a sorted sequence to try and implement a priority queue? So, now we are going to have a sequence in which the elements are sorted with increasing priorities. That is, the element with the smallest priority is sitting right at the front of our sequence. So, in which case minimum and delete min are just going to take a constant amount of time, right. Minimum element, as I said, is the element at the front of our sequence. So, we will just be able to retrieve the minimum element in constant time. Similarly, to delete it, we just have to delete the minimum element and then delete the minimum element from the front of the sequence. So, this is what your sequence would look like now. Note that the element with the minimum priority is sitting right at the front here. But now the problem is if you have to do the insert operation, if I have to insert, let us say, an element with priority 7, I will have to traverse this sequence till I come to the right position and put the element there. So, in the worst case, insert could now take order n time. Yeah. In this example, I am inserting 8, which can be inserted either before this 8 or after this 8, and in this case I am taking time proportional to the length of the sequence. So, priority queues find many applications. I gave you an example of scheduling. They are also used quite heavily in event simulation, in discrete event simulation, and they are used as a building blocks for many other algorithms. We are going to be seeing more algorithms in this course, let us say Dijkstra's algorithm, which would require a priority queue data structure to be able to efficiently implement the algorithm. And today what we are going to see is how to use a heap, a data structure called a heap, to implement a priority queue. So, we saw two methods to implement a priority queue, an unsorted sequence and a sorted sequence, and both of them had their problems. In the case of an unsorted sequence, the delete min operation and the minimum operation would take order n time, and in the case of a sorted sequence, the insert operation would take order n time, right, while the other operations were constant time operations. So, we would like to have a data structure which would insert all these, which would do all these three operations, insert, delete min and minimum, very efficiently. So, what is a heap? So, when we say heap, we typically mean what is called a binary heap. So, a binary heap is a binary tree that stores the priorities or the priority element pairs in the nodes, right. So, in the rest of this class I am just going to show the nodes as containing the priority of the element, and the element is sitting somewhere here also. So, they could be storing only the priorities or the priority element pairs. Now, the heap has two properties. So, one is the structural property. This binary tree, in this binary tree all levels are full. So, this is level 0. It can have only one node, it has one node. Level 1 can have 2 nodes, it has 2 nodes. Level 2 can have 4 nodes, it has 4 nodes. Level 3 can have 8 nodes, it has only 5 nodes. So, all levels except the last level are full, and the last level is what we will call left filled, which means that all the elements on the all the nodes on the last level are as left as possible. Right. So, there could be 8 elements there are only 5, but these 5 nodes would be the ones which are the first 5 if I were to move left to right. So, that is the structural property of a binary heap. The other property is what I call a heap property, and the heap property simply says the following: the priority of a node is at least as large as that of its parent. for any node, its priority has to be larger than the priority of its parent. So, this picture here does satisfy both of the properties, structural as well as heap. Consider any node, its priority is at least as large as the priority of its parent, right. You can take any node. I can restate this, I can also say it in the following manner: the priority of any node is less than or equal to the priority of its children. So, sometimes we will also think of it in this manner: priority of any node is less than or equal to the priority of its children. There might be two children, there might be only one child, as is the case here. In this case, the priority of this node has to be less than the priority of its lone child. So, let us look at examples which are not heap. So, this is not a heap, because if you look at this node, we require that it have a priority which is larger than the priority of its parent, at least as large as the priority of its parent, but its priority is 18, its parent's priority is 19. So, this violates the heap property. This does not violate the heap property, but as you can see, this node is empty, it is not. So, this last level is not left filled. We would like that if there were only 4 nodes at the last level, then they should appear as the first 4 nodes of this binary tree. They should appear as the first 4 nodes on the last level of this binary tree. Now, how does one find the minimum element in a heap? So, suppose I give you a heap. What is a heap? A heap, recall, has these two properties. One is a structural property, the other is a heap property. Suppose I give you a heap. How does one find the minimum element? The claim is that the minimum element, the element with the smallest priority, always sits at the top of the heap. By the top of the heap, I mean the node here at the root. And as you can see, such is the case in this picture. The element with the minimum priority is this element 11, and it is sitting at the top of the heap. Why is this the case? Why can't the minimum element not be somewhere else? Well, it is, if it is not at the root of the heap or at the top of the heap, it would be somewhere in the middle, somewhere inside the heap. But then it has a parent, and the heap property says that the priority of the parent is at least as large as the priority of that particular node. So, then the parent would have a larger priority. The priority of the parent is let me correct myself. The heap property says that the priority of the parent is no larger than the priority of the node. Now, if such is the case, then the parent would have an even smaller priority, and so the element that I was talking of was not the one with the smallest priority. So, just to recap what I said, if the element with the smallest priority was sitting elsewhere in the heap, then it would have a parent with smaller priority, and this would violate the heap property. So, this larger should really lead smaller, it would have a parent with smaller priority, and that would violate the heap property. Hence, the minimum can be done in constant time, because we just need to go to the root element to find the element with the smallest priority. What is the height of a heap? So, suppose I give you a heap on n nodes, what is its height going to be? So, recall our discussion on binary trees. If you have a complete binary tree of height h, then it has exactly 2 to the h plus 1 minus 1 nodes. If we have a heap of n nodes with height h, note that since the height of the heap is h, it has more nodes than a complete binary tree of height h minus 1. A complete binary tree of height h minus 1 has so many nodes in it. So, the number of nodes in the heap is larger than the number of nodes in a complete binary tree of height h minus 1. A complete binary tree of height h has 2 to the h plus 1 minus 1 nodes, and the number of nodes in our heap is less than or equal to this quantity. So, this inequality holds. N is strictly larger than 2 to the h minus 1 and less than or equal to 2 to the h plus 1 minus 1. So I can rephrase this as n equals the floor of log of h. This notation here really means that log of h, which need not be an integer, we are just rounding it down to the nearest integer. So I hope this is clear to everyone. The number of, okay, this is a mistake. This should read h equals log of n. So the height of a heap is log of the number of nodes. So just interchange this h and n, please. This is an error on this slide. So if n lies between 2 to the h and 2 to the h plus 1 minus a 1, then h is log of n. How does one implement a heap? So recall that till now we were saying that a heap is this kind of a binary tree. We can of course implement a heap using a binary tree, but it's much simpler to implement a heap using an array. So let's see what I mean here. So this is level 0 of the array, this is level 0 of my heap, this is level 1, level 2 and level 3 of the binary tree corresponding to this heap. So I'm going to put these nodes of the binary tree into an array with the root node sitting at the first location in the array. My array is going to be indexed starting from location 1. So 11 comes here, 17 and 13. So the next level would follow and we would go left to right. So 17 would be the next element, 13 would be the one after that, then 18, 21, 19, 17, 43, 23, 26. So this is level 0 of the binary tree, this is level 1 of the binary tree, this is level 2, this level, and this is level 3 of the binary tree. What's the advantage of putting the nodes of a heap into an array like this? So suppose I look at a node at location 5, let's say node 21, and I want to find out the parent of this node in the heap. Then all I have to do is take 5 divided by 2, take the floor. So 5 by 2 floor is 2. So the parent of 21 in this heap is going to be 17, which is the case here. You can do it for any other node. Let's take node 26. 26 is at location 10. 10 by 2 is 5, whose floor is also 5. So the parent of 26 is at location 5 and is 21. So you can quickly determine the parent of any node if you know the location of the node. So parent is just at location I by 2 if the node is at location I. Conversely, if a node is at location I and I want to figure out its 2 children, then the 2 children, the left child would be at location 2i and the right child would be at location 2i plus 1. Right? You can work out this math, it is very easy. I'll just show it with an example here. So if I look at node 13, it's at location 3, its 2 children then should be at location 6 and 7. 2 children are 19 and 17 and they are at location 6 and 7. Right? So given the location of any particular node, I can just quickly figure out what is the parent, what is the location of the parent, what are the location of the 2 children of that node. And those are the only things that I really need to do in a heap. And the heap property is really saying that if the element, so if I is a location, parent of I is the location of its parent, and A of parent of I, A is the array which is holding these priorities, so it's the priority of the parent of I. So the priority of a parent is less than or equal to the priority of the node itself. That's what the heap property is. So essentially we implicitly are maintaining the tree links. The parent-child relationships are getting implicitly maintained. The children of a node I are at locations 2i and 2i plus 1. And this is very useful, right? In binary, multiplying by 2 is just corresponds to a left shift, and multiplying by 2 and adding 1 is equally simple. So one can quickly figure out the children of a node or also the parent of a node by just doing one left or right shift and an increment operation. So this makes the operations really fast when you are trying to access the parent or the children of a particular node. Let's now see how one would insert an element into the heap. Till now the only operation we have seen is to find the minimum element in a heap, and that we said can be done in constant time because the minimum element in a heap always sits at the root of the heap. So suppose I wanted to insert 12 into this heap. What would I do? Well, right now this heap has 3, 7 and 12 nodes in it. If I insert 12, this heap is going to have 13 elements in it. If it has 13 elements in it, then structurally I should have another node here. So that's the first thing I would do. I would first create a node here, right? And let me now put 12 into it. Of course, structurally this does satisfy the structural property of a heap, but it's not a heap because it violates the heap property. This node should have lesser priority than its two children. It does not. It has higher priority than this child. So we need to take care of that. So since this has lesser priority than this, we need to swap this thing. We do that in this manner. We'll swap these two elements. Now the heap property is satisfied here, no problem. This has lower priority than its two children, but it's violated here. This does not have lower priority than its two children. So we should then swap this and this. We do that now. So the heap property is also now satisfied here. Now could it be, since we have changed the content of this node, could it be that the heap property is violated at this node? Let's look. This has priority 11, this has 17, this has 12. This has lesser priority than both its children. So the heap property is satisfied here, no problem at all. So we are done. We are done with the insertion of 12. So all we did was create a new node, put 12 here, and then move 12 up so as to maintain the heap property. So we saw that 12 had a lower priority than its parent, so we swapped 12 and its parent. Then once again we saw that 12 had reached here, 12 had a lower priority than its parent, so once again we swapped 12 and its parent. 12 now reached here, but now 12 does not have a lower priority than its parent, so we stop. Let's see if we were to insert another element. Let me insert 8 into this heap. So once again 8 would come at this location, so I put in 8 here. 8 now has a lower priority than its parent. This violates the heap property. So we would swap 8 and 17. Once again 8 has a lower priority than its parent. This node has a lower priority than its parent. So we would swap 8 and 12. Once again this has lower priority than its parent. So we would swap 8 and 11. And now we are done. This is now a heap with 8, the element that we inserted last, now coming at the root of the heap, and in fact it should come there because this is the minimum element, the minimum priority element in the entire heap. So let's look at insertion again from a slightly different point of view. So we again have the same heap as before, and we are trying to insert 12. So first we enlarge the heap, which means that we create the new node where 12, where we create a new node because we know that the new heap now has 13 elements in it. Sorry, it has 13 elements in it, and so this is what its structure should be like. Now we consider the path from the root to the inserted node, which is this light colored path. So this was the inserted node, and we just march up, we just go from this node to its parent, to its parent, and to its parent. So this is the path from the root to the inserted node. And on this path we find the topmost element with priority higher than the priority of the inserted element. So what are the nodes on this path, these are these 3 nodes, they have priorities 19, 13 and 11. The topmost element on this path with higher priority, the element we are inserting is priority 12. The topmost element, so this is the topmost element, but it has priority lesser than 12. This is the next highest element, but this has priority and this has priority more than 12. So this is the topmost element on the path with higher priority than that of the inserted element. So this is the element. So what are we going to do now? We are going to insert 12 at this location, but where would 13 go? 13 would get pushed down. And where would 19 go? 19 would get pushed down, like this. So this is exactly the same procedure as before. If you look at the slide that we got earlier, the elements were at the same location, except there we started with 12 here and we bubbled it up. Now I am saying that I am going to directly figure out where 12 is going to come and I am going to move elements down. Let us argue correctness. Let us argue that this procedure of insertion is really correct. And for this we will look at this other view of insertion that we saw on the previous slide. So the first claim is that the only nodes whose content changes are the ones on this path. This is the path that we considered, which is the path from the newly inserted node to the root, and we are changing only the contents of this. So we are in fact only changing the contents of this part of the path. So if the heap property is getting violated, the heap property can be violated only at the children of these nodes. It could be that for this node, since we are modifying this content, it might be that the new priority of the parent is larger than the priority of this guy, or the new priority of this of the parent of this node is larger than the priority of this guy. That would be a violation of the heap property. So it is only for these two pink colored nodes that the heap property might be violated. But what is happening? What are the new contents of 31 and what are the new contents of the parents of 31 and 17? Right? 31 is 19. What is the new content of this going to be? Well, if you recall, 19 was getting moved down, 13 was coming here and 12 was reaching there. So the new content of this node is 13 and not 9 is 13, which is only going to be less than this. So the new contents of any node are only going to be either the newly inserted element or the parent of that node. The new content of this is going to be the content of its parent, and the content of the parent is already smaller, already has a lower priority than the priority of this guy. So the priority of each node is only going to reduce. So the priority of this guy is going to reduce because 13 is going to move here. The priority of this guy is going to reduce because the newly inserted element 12 is going to come here. And recall from our choice of path that this was picked as a node with higher priority than the priority of the element that was getting inserted. So since this is higher than this, the priority of this is also going to reduce as a consequence of the insertion procedure. So the priority of all of these nodes are only going to reduce as a consequence of the insertion procedure, and hence the heap property would not get violated. So these are going to be the new priorities of these nodes. We said that the heap property could be violated for this guy or for this guy. They should also have been pinged. It could be violated for this or this, but earlier its parent had a priority 19, now it has a priority 13. Earlier the parent of this guy had a priority of 13, now it has a priority of 12. So priorities are only reducing, and if they are only reducing, then if earlier this had a priority which was smaller than the priority of this guy, it continues to have a priority which is smaller than the priority of this guy. If earlier this had a priority which is smaller than that of this guy, it continues to have a priority which is smaller than the priority of this guy. So the heap property is not violated at all, and so insertion, so what we get after insertion is still a heap. I am now going to look at another procedure called heapify, which we are going to use as I mentioned at the beginning of the class, we are going to use for the other methods that we have to do on a heap. So I am now assuming that my heap is kept in an array A, and I is an index into this array. So heapify takes as parameters an index into the array A. Now the binary tree is rooted at the two children of I. Left I and right I are the two children of I. The binary trees rooted at these two locations are, let's say, already heaps. But it might be the case that the heap property is violated at this node I, that is A sub AI might be larger than its children. This should actually read larger, so that it is violating the heap property. So AI might be larger than its children, and thus violates the heap property. So now heapify is a method which tries to maintain the heap property, makes the binary tree rooted at I a heap by suitable modification, and we will see what this is in a second. So let us look at this structure. This is not a heap, because this node right here at the very top has priority which is larger than the priorities of its two children. Yeah, but this binary tree, if I were to just restrict myself to this part, right, is a heap. Why? It does satisfy the heap property. Every node has a priority which is smaller than the priority of its two children. This has smaller priority than its two children, this has smaller priority than its two children, this has smaller priority than its two children. Similarly, this here is a heap. Structurally as well as it does satisfy the heap property. Each node has priority smaller than its two children. So these two are already heaps. But this entire thing is not a heap, because the heap property is getting violated at this node. This does not have priority smaller than the priority of its two children. And somehow we want to make this entire thing a heap. So we can invoke the heapify procedure. So the heap property is violated at node with index 1, which is this node, but the subtree is rooted at 2, 2 is this and 3 is this. So the subtree is rooted at 2, which is this, and this are heaps. So we would invoke the heapify procedure with 1, because we want to make this a heap. We want to make this entire thing a heap. So we would invoke heapify with 1. Right. So for heapify, remember, we require that whichever node heapify is invoked on, the two children of this, the subtree is rooted at the two children of that node are already heaps. That is a very crucial part for heapify. Only then would heapify work. So if heapify is invoked at 1, it can be invoked at 1 only because the subtree is rooted at the two children of node 1, this and this, the subtrees rooted here are already heaps. So let us see how heapify works. Heapify is going to look at the two children of this node where the heap property is currently violated. It would look at the two children, which are these 10 and 11, and it would take the smaller of these two children and swap it with 17. So the smaller is 10, it would swap 10 with 17. So now the heap property the heap property is valid at this node. This has priority less than the priority of its two children, but the heap property is not is violated at this node now, because this does not have priority smaller than the priority of these two children. So once again we are going to do the same thing. We are going to look at the two children, take the smaller one amongst them, which is 16, and swap it with this. So the heap property is now valid at this node. But is the heap property valid at this node, because we also change the content of this node? It is, because now when I look at the two children of this, they are 23 and 43, both of which have priority higher than 17, and so the heap property is valid here. And so now this entire thing is a heap. This is a heap because the heap property is now valid at every node in this tree. We have, recall, changed only the contents of these nodes. So that is the heapify procedure. So once again, to recap, heapify can be done, the heapify procedure can be invoked at a node I only if the two children of this node or the subtrees rooted at the two children of this node are already heaps. So once again, we'll present a second view of heapify, which will help us prove the correctness of heapify very easily. So heapify essentially is tracing a path down the tree. In our previous example, this path was this blue colored nodes. These were the nodes whose contents we modified. If I look at the last node on the path, suppose I call it node j, then the left and the right child of j have priority which was larger than the priority of node I. I is this node, I in our example is 1. So 43 and 23 are both larger than 17. And another property is that all elements on this path have lower priority than their siblings, right. So what are the siblings? Sibling of 16 is 21, sibling of 10 is 11, 17 does not really have a sibling. So 10 is less than 11, 16 is less than 21. And why is this true? Why is it the case that the priorities on this path are less than for all nodes on this path have priorities less than the priority of the sibling? That is because of our choice of the path. We went left here, we came left because because we compared 10 and 11 and we picked 10, so that we could then swap it with here. And then when we came here, we compared 16 and 21 and we picked 16. So just from the way we constructed our path, this statement really follows. Now what are we really doing in heapify? In heapify, what we are really doing is that we are moving these elements up. Let me show you how. If you look at, so I'm just showing it in one step now, but what we saw earlier was a sequence of steps. So this was the net result. The 10 moved up, 16 moved up, and this 17 really came at location j. It came at this location. Right? This was the net result of our heapify step. So now once again the same thing is happening. Right? 16 was here, it was less than its sibling, and it moved up here. So now 16 is less than 21. Similarly 10 was less than 11, 10 was less than its sibling, 10 moved up here. So now it has priority less than its child. And 17, which was here, which was at the root came here, but because of this property that the last node on the path has both of its children have priorities which are larger than ai, so 17 is going to have lower priority than both of these. So while the contents of these three nodes have changed, the heap property is satisfied at all of these three nodes. This is going to have lesser priority than its two children because of this property we mentioned here. This is going to have lesser priority than its two children because this priority, that's this 16 which was here, which was earlier a sibling of 21, had a lesser priority than 21, and now it's become a parent. And similarly for 10 will have a lesser priority than this guy because this was the smaller priority node amongst the two siblings, 10 and 11. So this essentially establishes the correctness of the heapify procedure. What you get as a result of heapify is still a heap. So heapify is really a mechanism to rebuild a heap. So if due to our operations the heap property is violated at a particular node, then we can heapify at that particular node. So assuming of course that the two subtrees the two child subtrees which are rooted at that node have the heap property, then we can do heapify on that node and get a larger heap. So, let us do a quick runtime analysis of the various procedures we have seen today. So, recall that a heap of n nodes has height order log n. When we are inserting an element, the insertion procedure was that we would create a new node and then we would move the element up the heap. In the worst case, the element might move all the way up to the top. If it moves all the way up to the top, then we require time proportional to the height of the heap. But an n node heap has height at most log n. So, we require at most order log n steps to do an insertion. The other procedure we looked at today was the heapify procedure. In the heapify procedure, on the other hand, the element moved down the heap. We took the element, so if we are invoking heapify at node I, we looked at node I, we looked at the two children of node I, we took the smaller of the two children and swapped it with node I, and continued the process till the element came down and the heap property was eventually satisfied. So, in the worst case, the element might move down as many steps as the height of the heap, but the height of the heap is only order log n. So, in the worst case, the time taken for heapify is also order log n. So, the two operations that we looked today, insert and heapify, both require only order log n time. We also looked at the operation of minimum, which was just find the minimum element in the heap without removing it. So, just to find the minimum element, we could do it in constant time, because all we had to do was to go to the root element of the heap and return the value of that, return the element stored at the root. So, minimum takes constant time and insertion takes order log n time. Heapify also takes order log n time, and we are going to, in the next class, use heapify to remove the minimum element from the heap, and we will be able to do that in order log n time too. So, with that we end today's discussion. In the next class we are going to see how to use heapify to remove the minimum element, the delete min operation. We are also going to see how to create a heap quickly in order n time, and we are going to see how heaps can be used to do sorting efficiently. Thank you.